All right. Yep, another question.
I'm sorry, can you repeat the specific parts that are not going to be on the exam? Because I know you said you want to draw orbital diagrams.
Yes, so you won't have to draw a molecular orbital diagram. You may have to fill in electrons and calculate bond order, but the structure of it would be provided. There's one other thing. You don't need to know that certain diatomics have the pi orbitals lower energy than the sigma. That content won't be on the assessment. I think that's everything that I've said. I'll post an announcement as well, just to make sure everyone has access to that information. All right, so this question here, we are ranking from low vapor pressure to high vapor pressure, pure substances of each of these three molecules. So a sample of butane, sample of acetic acid, and a sample of 2-propanol. Remember that vapor pressure is the amount of gas above the surface of a liquid. So as any liquid, some of these molecules are remaining as a liquid, but some of them have high enough energy to evaporate as a gas, and at the same time, gaseous molecules are condensing back down to be a liquid. So if that liquid sample has stronger intermolecular forces, stronger forces holding those molecules together, then fewer of those liquid molecules are going to evaporate as a gas. So stronger intermolecular forces, we wrote this on the next slide, those molecules that have stronger intermolecular forces in the liquid phase will have a lower vapor pressure because fewer gaseous molecules will be present. So if we're completing this question, we need to consider what intermolecular forces are present between these molecules. So butane is all carbons and hydrogens. Carbon to hydrogen bond is not polar. They have very similar electronegativities. So this is overall a non-polar molecule. I'm not going to write that. I actually just want to write dispersion. So the strongest intermolecular force between butane molecules is dispersion forces. Acetic acid, we have a hydrogen bonded to an oxygen. So this can have hydrogen bonding, intermolecular forces. And in 2-propanol, we also have an oxygen bonded to hydrogen. So this can also have hydrogen bonding. So we can get one of these out of the way. Butane has the weakest intermolecular forces. Weaker intermolecular forces in the liquid phase means it's easier for butane liquid molecules to evaporate into a gaseous phase, so there will be more gaseous phase butane molecules at the surface of a butane liquid, which means it has a higher vapor pressure. More molecules in the vapor phase, higher vapor pressure. So butane has the highest of these three, due to weaker intermolecular forces. Between 2-propanol and acetic acid, they both have hydrogen bonding interactions. So we need to consider at how many locations on the molecule can hydrogen bonding interactions occur. So between two acetic acid molecules, or more than one acetic acid molecule, that hydrogen bonded to oxygen can hydrogen bond with another oxygen from another molecule. Those are just bonds. So there's one hydrogen bonding interaction. The oxygen bonded to hydrogen can have a hydrogen bonding interaction with another hydrogen from another molecule. And the oxygen with a double bond can also have a hydrogen bonding interaction with a hydrogen from another acetic acid molecule that is bonded to an oxygen. So there's three locations, 3 atoms in acetic acid that can participate in a hydrogen bonding interaction. In 2-propanol, there's only 2. We have the hydrogen that's bonded to oxygen, can have a hydrogen bonding interaction with the oxygen from another propanol. And the oxygen there bonded to hydrogen can have a hydrogen bonding interaction with the hydrogen bonded to oxygen in another propanol molecule. So acetic acid, between acetic acid molecules, there can be 3 locations where hydrogen bonding interactions can occur. In 2-propanol, there's only 2 locations where hydrogen bonding interactions can occur. So in acetic acid, those molecules are held closer together because of that greater number of hydrogen bonding interactions. They're held closer together, that's a stronger intermolecular force, so lowest vapor pressure. So acetic acid is lower, and then 2-propanol is higher than acetic acid, but still lower than butane. And then if we're thinking about boiling point, think about acetic acid. It has 3 locations where there are hydrogen bonding interactions can occur between molecules. Strongest intermolecular force. A boiling point, a higher or lower boiling point, is related to the strength of intermolecular forces. Remember, if you're boiling something, that substance is going from a liquid phase to a gas phase. So if you have liquid molecules held stronger to each other, it will require more energy for those liquid molecules to break those intermolecular forces and enter the gas phase. So stronger intermolecular forces means higher boiling point, higher temperature at which boiling will occur. I'm just going to write BP for boiling point. So high boiling point on the left and low boiling point on the right. Yeah, go ahead.
So in the second one, how's the oxygen bond with carbon and hydrogen bonding?
So that is still an electronegative. Oxygen is still electronegative, and it can participate in a hydrogen bond with a partial positive hydrogen that's bonded to an oxygen.
So like hydrogen bonding doesn't need to like atomically bond to hydrogen.
The hydrogen, right? Yeah, the hydrogen has to be bonded to the electronegative element, but we can also observe hydrogen bonding between where the electronegative element that adheres to the hydrogen bond might not be bonded to hydrogen. So remember when we have a closed system, we have a liquid, let's just say we're pouring a liquid into a beaker and then closing it. That liquid would start to evaporate. There's always going to be some gaseous particles at the surface of the liquid. And then as the liquid molecules evaporate and vapor is starting to form, condensation can then occur. We can't have condensation until we have gaseous molecules. So condensation can occur, but that will occur at a slow rate until that liquid starts building up more and more gas molecules. And then as it continues building and evaporating molecules into the gas phase, condensation is occurring as well. And this reaches a state that we call dynamic equilibrium, which means that at one point in time, there is a constant vapor pressure. If you have a closed system, there's a constant vapor pressure. But that doesn't mean that the specific molecules that are in the gas phase remain in the gas phase. There's constantly some gaseous molecules condensing to become a liquid again, and some liquid molecules evaporating to become a gas. So dynamic equilibrium means that we have the condensation rate, so the rate at which a gas particle becomes a liquid, and the evaporation rate, the rate at which a liquid becomes a gas. Those rates are equal. So we have the same concentration of gas over time, same concentration of liquid over time, but it's not the same exact molecules. They're constantly flipping with each other. That's what we mean by dynamic equilibrium. All right. Questions on vapor pressure, or boiling point, or intermolecular forces? Okay. Then we are going to move to the Clausius-Clapeyron equation. So before we talk about what this equation is, if you think about a substance has a certain vapor pressure, if you add energy or add heat to that liquid, then more of those liquid particles have energy that can then escape into the gas phase. And so as temperature increases, vapor pressure increases. There's a graph here that shows as you increase temperature of a liquid, so this red line is ether, here's ethanol or ethyl alcohol. As temperature increases, the vapor pressure increases in this slope, so it's not a straight line, but we have the slope here, until it reaches boiling point, and then that's when the molecule starts to boil. This is when vapor pressure, so this line is equal to atmospheric pressure, 760 millimeters of mercury. So as temperature changes, the vapor pressure of these different liquids changes. But this line is not a straight line, so it's not convenient to work with. We can manipulate this to have a straight line. So if we plot the natural log, a function in your calculator, of vapor pressure in the y-axis, and 1 over temperature in the x-axis, we achieve a straight line with a slope that's equal to negative heat of vaporization over R. So this Clausius-Clapeyron equation, we're going to look at 2 versions and only really use one of them in our class. But this is used to calculate the enthalpy of vaporization of a substance by measuring its vapor pressure at different temperatures. So if you're working in a lab, you can't really look at or manipulate something and directly measure its energy required to vaporize, but you can directly measure how much temperature you provide and how much vapor pressure that substance has. So with that experimental data, that can be used to calculate the heat of vaporization. So the Clausius-Clapeyron equation takes all of that into account. We have an equation that's in the y equals mx plus b formula, where we have natural log, ln is natural log, a function in your calculator, pVap is vapor pressure, delta HVAP is enthalpy of vaporization, or heat of vaporization. R is the gas constant. Heat of vaporization, we're talking about energy in units of joules. So for this equation, we use the gas constant in units of joules per mole Kelvin. You have both provided on your periodic table sheet. For this equation, you have to use the 8.3145 joules per mole times Kelvin. That means for this equation to work, you need enthalpy of vaporization in joules per mole. Sometimes it's provided in kilojoules per mole, or joules per gram, or kilojoules per gram. So you just have to make sure that it's in joules per mole. Capital T is temperature. It must be in units of Kelvin because we're using Kelvin in the gas constant. And then natural log of beta. This is a constant that is unique to each liquid. So each liquid substance has its own beta, and then you can take that natural log of that constant. So if we're thinking about doing this in a lab, the problem here is that you have to know what that constant is to be able to solve this equation. That might not be readily available. It's also not something to measure directly. So there's a different version of this equation. Units and everything are the same, but it takes 2 points, so 2 xy or T1 or T and P, temperature and pressure, relates them together and then put it into this equation. And this allows for the calculation of delta H vap by measuring vapor pressure and temperature at 2 different points. So this equation, you don't need it for Friday, but on future exams, just so you know, looking at the periodic table sheet, it is this equation here, except for this E is delta H of vaporization, and this is P2 over P1. So same relationship. We have T1 and T2, just changing these variables a little bit. But just so you know, that one is provided. Again, you don't need it for Friday, so don't worry. But this is the equation we'll use for our calculation. So we're going to use the Clausius-Clapeyron 2-point version in the next 2 learning checks. But do me a favor and go to this learning check first, the one with the table. This one's a little bit more straightforward, and then we'll do the one before it. So we have a table of some substance. We don't know what the substance is, but we're looking to calculate delta H of vaporization. We have pressure and temperature at we have the pressure at 2 different temperatures. So we'll label the first row as 1, second row as 2, and we'll go ahead and use this equation. So natural log of P2 over P1 equal to delta H of vaporization over R times 1 over T1 minus 1 over T2. Well, we can start plugging in values. We have P1 and P2. We have T1 and T2. So we can do natural log of P2, so 720 torr, divided by P1, 450 torr. We're calculating delta H of vaporization, so we don't know that value. We'll keep that variable in. R is the universal gas constant, 8.3145 joules per mole Kelvin. And then 1 over T1, which is 270 Kelvin, minus 1 over T2, 370. So in your calculator, you have the natural log function. You can click that number and put in 720 over 450. Other calculators, you need to put in the fraction first and then press natural log. You just have to figure out how your calculator works.
I think to use the 450
Over here? Okay, good question. So in the table, we're provided natural log of vapor pressure. So this fraction, or natural log of P2 over P1, if you have natural log of any fraction, let's just do x over y. This is equal to the natural log of x minus the natural log of y. So you could, instead of doing natural log of the fraction, do natural log of 720, or P2, which is 6.58, minus natural log of 450, which is 6.1. Both should give you the same number.
So if we use the other numbers, we have to subtract them, we would have to.
Yeah. Right. So if we use those values, I'll just go ahead and put those in. So natural log of 720, 6.58, minus natural log of 450, 6.11. This is equal to delta H of vaporization divided by gas constant. And then we're also provided in the table, you might not always be given this, but because you can calculate it, but 1 over 270, 1 over T1 is 0.0037. Units are per Kelvin. Kelvin is in the denominator. All right, so simplifying the left side, we have 0.47 torr is equal to delta H of vaporization times this value, 0.0037 minus 0.0027, divided by 8.314. Our goal with solving this equation is to get our variable on its own. So I'm simplifying all the values on the right, all the values on the left. So this is so here we have a value equals our variable multiplied by a fraction. We divide both sides by this fraction, then we'll have delta H on its own, and that value is 3,907.81 joules per mole. As far as which order of steps you use when you're simplifying, once you have all the values in and you're simplifying the equation, there's different ways that you can do it, right? You don't have to do ln of P1 minus ln of P2. You can just take the natural log of the fraction. That would be fine. You should still get that value. You could multiply both sides by 8.314 and then divide by this value. That's also fine. If some other process makes more sense to you, you could try it out and make sure you're getting the same answer. There are multiple ways to do it correctly, but you could also do it incorrectly, and you don't want to do that. Questions on this one? All right, we're going to do the previous slide. So in this example, we are looking for vapor pressure. So we're looking for a pressure value. The statement says methanol has a normal boiling point of 64.6 degrees Celsius and a heat of vaporization of 35.2 kilojoules per mole. So we know delta H vaporization. What's the vapor pressure of methanol at 25 degrees Celsius? And we're looking for millimeters of mercury. So different pressure unit. We're using the same equation. We're solving for a pressure value. So we must have all the other information that's needed. In that first statement, methanol has a normal boiling point of 64.6 degrees Celsius. Gives you more information that you might immediately see. Remember that for something to boil, its vapor pressure equals atmospheric pressure. So if something has a normal boiling point of 64.6 degrees Celsius, that means that at that temperature, its vapor pressure is 1 atmosphere, or its vapor pressure is 760 millimeters of mercury. So if you know the boiling point of a substance, you know its vapor pressure at that substance, it's atmospheric pressure. And then we're looking for its vapor pressure at 25 degrees Celsius. So let's write out what we know. We'll have a T1 and P1 pairing. We'll have a T2 and P2 pair. And then we'll have delta H of vaporization. Those are all all 5 of the variables in that equation. So let's set T1 at the goal, 25.00 degrees Celsius. The equation will still work if you switch the pairing of T1 and P1 with T2 and P2, as long as you keep the pressure and temperature that align with each other together. You'll still get the same answer. So P1, the pressure that we're looking for, we don't know. We'll leave that as X, and that will be in millimeters of mercury. T2 is the boiling point, 64.6 degrees Celsius. And P2, since this is the boiling point, the vapor pressure at that temperature is atmospheric pressure, or 760 millimeters of mercury. So that pressure conversion we learned last term. I think what's on the periodic table sheet is that 1 atmosphere equals 760 torr, but a torr is equal to a millimeter of mercury. So 1 atmosphere is 760 millimeters of mercury. All right, now we have delta H, heat of vaporization. This is 35.2 kilojoules per mole. All right, so using the equation, we have natural log, we're just going to rewrite it here, P2 over P1 equals delta H of vaporization over R times 1 over T1 minus 1 over T2. So we have all values except for P1, but we have to manipulate some of these values before we can use the equation. What's one thing we've got to change? We need to change kilojoules to joules. Why do we need to do that? There we go. Yes, the gas constant R is in units of joules per mole Kelvin. So we need our energy unit to be joules. So we need to convert 35.2 kilojoules per mole to joules per mole. And that is 35,200 joules per mole. So we're multiplying by 1,000. Someone else tell me what else we need to change. Yeah. Celsius to Kelvin. Is that what you were going to say? Yeah. Two hands in the same area. We need to change degrees Celsius to Kelvin. So 25 degrees Celsius is equal to 298.15 Kelvin. And 64.6 degrees Celsius is 337.75 Kelvin. Okay, we can start plugging values in. But we don't know P1. And once this is in the fraction with natural log, if we're just looking for 1, it's actually helpful to separate this into that subtraction, where we do natural log of P2 minus natural log of P1. So natural log of P2, we have P2, 760. I'm going to leave units out because this is a long equation. But we have natural log of 760 minus natural log of P1, and that's what we're looking for. So we'll use X for that. This is equal to delta H of vaporization in units of joules per mole. Divided by gas constant, 8.3145 joules per mole Kelvin. Times 1 over T1, 298.15. Oh, I said I was going to leave units out. And then minus 1 over T2, 337.75. On the left side of the equation, in the calculator, we can find the natural log of 760. That is 6.633. So we have 6.633 minus natural log of x is equal to the right side of the equation. All we have here are numbers, so we can simplify this whole right side. Remember that you have to do what's in parentheses first. So you do 1 over 298.15 minus 1 over 337.5, multiplied by the numerator, divided by the denominator. And that whole right side is equal to 1.6648. All right, we need to continue working towards getting the variable on one side of the equation by itself. Right now we have 6.633 minus natural log of the variable. So let's subtract 6.633 from both sides. That will cancel it out on the left, and then we're moving that value to the right. So we have negative natural log of x equals, if you subtract 6.633, that is 4.9682, negative 4.9682. Both sides are negative, so you can multiply by -1, divide by -1 on both sides, and that will convert them both to being positive. To save room, I'm just going to erase that negative sign. So if negative natural log of x equals negative 4.9682, then positive natural log of x equals positive 4.9682. Okay. Now we need to use the counter function for natural log to get x outside of the natural log. Yeah. Yes, it's e. So the counter function for natural log is e. If you raise e to the natural log of x, this is another function on your calculator, is e. E to the natural log of x is just equal to x. So the natural log and the e cancel each other out, we just have x. So if we take e to the natural log of x on the right, then we have to take e to the power of 4.9682. And that will give us our final answer. That will give you a numerical value. This is 143.8. What are the units here? Millimeters of mercury. Yeah, this is a rather complicated equation. It's still helpful to keep in your units if you have sufficient space. But anytime you complete a problem like this, you have to report your units. So X is 143.8. We're looking for pressure in units of millimeters of mercury. We used millimeters of mercury for P2, so we have the same unit for P1. So the unit here is millimeters of mercury. If, for example, we said normal boiling point means that occurs at a pressure of 1 atmosphere, and we said P2 is equal to 1 atmosphere, that's equal to 760 millimeters of mercury, we would get some value, but then to report it in millimeters of mercury, you need to convert that atmosphere value to millimeters of mercury. One more thing to conceptually think about is if this answer makes sense. So at 64.6 degrees Celsius, the vapor pressure of methanol is 760 millimeters of mercury. We're looking for the vapor pressure at 25 degrees Celsius. So we're decreasing the temperature. We're decreasing the temperature. We're decreasing the amount of energy those liquid particles have, which should decrease the amount of gas particles in the vapor above the surface of the liquid. So we should have a lower vapor pressure. And we did calculate a lower vapor pressure. So that checks out. Okay, other questions on this equation? All right, then we will go to the next section on phase diagrams. So phase diagrams, there's a different diagram for different substances, and they relate the solid, liquid, and gas phases of these substances. So here's one example. This shows bottom right side is gas for a substance. Middle is liquid, and the left side is solid. Now notice that the x-axis is temperature, and the y-axis is pressure. So if you're at any temperature any pressure as you increase in temperature, then you might start as a solid at cold temperatures. It's a solid, then it may convert into a liquid and then a gas. If you're at a certain temperature, and you're increasing pressure, then you will go from a gas to a liquid or gas to a solid. Now the intersection of these different components, so solid and liquid, this line here shows from solid to liquid, melting, or liquid to solid, freezing. Liquid to gas, vaporization, gas to liquid, condensation. Solid to gas, sublimation, gas to solid, deposition. And we're at different temperatures and pressures, but usually on a phase diagram, there will be a horizontal line that tells you where or how the substance exists, in what phases, at what temperatures, at 1 atm or the atmospheric pressure. So if you trace this pressure, 1 atmosphere across, at low temperatures, substance is a solid. As the temperature increases, we have the normal melting point, that's this right here. This is where the substance becomes a liquid at 1 atmosphere. And then as you increase in temperature, increase in energy, you eventually will hit the normal boiling point where the liquid becomes a gas. The triple point is the temperature and pressure at which all 3 phases exist in equilibrium. So both, or all solid, liquid, and gas can exist at equilibrium at that temperature and pressure. And then the critical point is a point where past that, at higher temperatures, the substance is called a supercritical fluid. We'll define that on the next slide. But phase diagrams with more detailed information can exist or they do exist for different substances. So the triple point, this slide points out some key features. So triple point is where all 3 phases we already have phases. All 3 phases of the substance are at equilibrium. The critical point is the pressure and temperature conditions above which the substance no longer exists as a gas or a liquid. But as a supercritical fluid. And a supercritical fluid, I don't have an example of this, but I'll try to get one for Monday. This is a 4th phase that has properties common to both liquids and gases. So it can diffuse through solids as gases can, but can also dissolve substances like liquids can. All right, let's do this learning check here. So you have 3 iClicker questions related to the phase diagram. It's just a generic phase diagram that's on the next slide. Identifying phases in different regions, where solid and gas are in equilibrium, so which line, and then which arrow, in the 3rd question, which arrow points to the normal boiling point of that substance. right, we'll review this on Monday. But I'll see you here on on Friday. Days are mixed up. Thanks. Oh, yeah, so it is, that's a good point, I wasn't, paying attention to sig figs. It's good to just look back and use how many sig figs are included as like a general rule of thumb. Yeah, you're welcome.
So you said there would be like three short answers. So if there was like a bond diagram, like consolidated like in one order, that would be the short answer, right?
Yeah, that would be, well, that could be in a multiple choice question.
Okay, but if we had to like actually fill it out like
Yes,
ourselves.
right, so that would be short answer, if you're calculating bond order, that could be a multiple choice question, or all of that together could be short answer.
Okay. Have a nice day.
Thanks, you too. Yeah.
I can like obviously adjust to my schedule. Like I'll but this Friday I don't think I can be here. The reason is, I don't know if you remember last semester I forgot to go to court for my citizenship.
Oh, okay, yeah,
This Friday it's when I go and finish my passport and whatnot.
okay,
And like the documents has to be finished as soon as possible for me to be valid basically.
okay,
I don't know if you've noticed I changed my name on like it used to be Oshrock, now it's Shira.
okay.
So would I be able to? I don't know. I've always taken everything
Yeah.
on the day, so I don't know how it's.
So what is, let me actually end the, oh, did everyone submit? Yeah. Let me end the recording so we don't have this conversation
Oh, yeah?
over that.
Thank you.